All right, hell yeah. So we're going over strain and we're going over beam bending. So you can just imagine this is a ruler and we're going to twist, use our fingers to apply a twisting force on both sides. That's a moment. And we get this thing to bend. And so what happens is that it forms, if we have pure bending, it forms the arc of a circle. And then so we just use, so this problem is just going to be trigonometry. But we do have one part of this example problem, you know what I mean, that we have to use this equation that we did a derivation of. The strain is going to be a function of the distance from the neutral axis. This is y. So this is an equation, you know what I mean? But y is our independent variable. So, and sometimes when you're doing math, that can throw you for a loop. But anyway, so we have, and strain also is kind of a funky little thing because it's the change in length divided by the original length. And I like to think of that as a percent change in length. And it can be negative if things get shorter. It can be positive if things get longer. And what we do is we set up this value for the radius of the circle, and we say 1 over the radius is curvature. And so we can take a look at that, and we say that if we have if the beam is smiling at us like a smiley face, the radius will be positive. And why this is that we always set our y-axis going to be vertical up or positive up. So that's where we set our y-axis, and the x-axis is always going to be to the right. Cool. So my goal is to actually just walk my way through here. I've not even seen this one, but the whole goal is to read textbooks and see if we can follow along. All right, so a simply supported steel beam from A to B, and this is figure 5.8a. Sometimes they'll reference a bunch of different figures, and in this one we have 5.8a, 5.8b, so it's just good to see okay, here's figure A, and that's the beam with 2 moments on it. Figure B is the actual, hey, this is part of a circle, and now we have, some sort of angle. In this case, they do 2 angles, and we have a length. I guess this is the length. I guess you'd call that a chord, but we do have arc length, man. And that's one where it's just you can enter engineering and just kind of forget that. I don't know. It's why is the equation for arc length just seem bizarre to me, or just I didn't do enough problems and I graduated with probably without knowing the equation for arc length. But when theta's in radians, arc length is just this angle in radians times the radius. Cool. So we're going to be looking at that. But let's get reading, because the whole goal is to just read our way through here and see if we can follow along. So hell yeah. So this figure 5.8a has a steel beam from A to B. It's steel. Cool. It has a length of 8 feet. You know, I mean, we might have to change that to inches. So 8 times 12. Definitely don't know that one. What was it, 96? How would I do 8 times 12? We can pause on that one. It's 4 times 24. Does that help me? Hell yeah, 4 times 24 helps me, because 4 times 25 is 100, minus 4 is 96. So, hey, that was pretty decent to get there pretty fast. All right, and the beam has a total height of 6 inches. See how we need to work in inches? So everything's got to be in inches. This is 96 inches in length. All right, so with our equation, we have a strain that's a function of y, and this y has to start at the neutral axis. So where we put our y value is right in the middle of the beam. And so let's go back to this picture, you know what I mean? Because this is what you'd be looking at. So we have our neutral axis. It does not change length. So we take an unbent beam, and we take a little small section of it, or we could take the entire length if we wanted to. It doesn't really matter. But what happens is that the top crunches in, it shortens. That's going to be that strain equation. It's going to have a negative strain. And the bottom is going to have a positive change in length that's going to lengthen. But that means that somewhere it doesn't do either. It stays the same length. So the length of the beam won't change. And that's going to be where we put our neutral axes. And so that's where this strain equation comes from. If it's just a rectangular beam, that's going to be right in the middle. It's at the centroid. And so let's talk about that, because if we throw in a positive value of y, curvature is going to be positive because we said rho is going to be in the positive y direction. But hey, we get a negative value for our strain. Yeah, because it's shortened. So when we have a smiley face, the top shortens. That's going to be a positive value of y. And we need to get back to this. You know what I mean? The whole point is just to keep reading and not make an hour-long video. So we're shooting for about 20-25 minutes, maybe half hour. All right, so cool. So a height of 6 inches is bent, and is bent by these couples m naught. And, you know what I mean? Don't forget that a moment or a couple is two forces. So you could just, every time you see this little curve in a moment, you know, just put a downward arrow and an upward arrow in the direction that the moment would be, and then just separate it by a small little distance. You know what I mean? Sometimes that's mentally a little bit easier to understand what a moment is. And it's still a load. It's still a force. Two forces that are opposing separated by a distance. All right, and that's going to cause this to be bent in a circular arc, and I mentioned that. It's a pure circle because, you know, watch the derivation videos. The whole point is just to, man, I struggle at just getting to it. So with a downward deflection, hell yeah. So we're going to have an arc, and we're going to have a downward deflection. That's what this picture is. And using trigonometry shouldn't be that hard. You know what I mean? Here's the radius from the beam to here. Here's the radius from the beam to there. Hell yeah. You know what I mean? Like, how hard could it be? It seems like it's going to be hard. I don't, yeah, like, just mentally, I'm just like, I don't know. Cool. And so the longitudinal normal strain, that's going to be the change in length in the x direction. Elongation, and it's going to elongate on the bottom surface. We talked about that with the smiley face. And the elongation on the bottom surface is 0.00125. So elongation. So the strain is, what are they doing to us? It says the I can't say that, but that longitudinal normal strain, I think, oh, damn it. See, they do parentheses elongation. Yes and no. Change in length, I consider elongation. And, you know what I mean? And I guess this is where I got to check myself before I wreck myself, because strain is a bizarre little term. And it's going to be change in length divided by the initial length. I just talked about that. It's a percent or a fractional change in length. And I call it elongation all day long. Hell yeah, strain is changes in length. It's but the equation for strain is change in length divided by length. So it's not just, if elongation is change in length, if that's what we're saying elongation is, it's not equal to strain. If they're saying elongation is change in length divided by length, and that's strain, sure, we're on the right track. So we need to see, like, because that's two different things. So this is strain, because if it's steel can take a 0.002 fractional change in length. You multiply this by 100, move the decimal places 2, and you get, steel can do 0.2%. So this shows a 0.125%, and if it was 0.1, we're just like half. Our load is, you know, we could put twice as much bending moment on this beam if we wanted to. That's what that would say. If the bottom surface had a strain of 0.002, well, it's right at the yield, kind of that plastic point. We might experience a little bit of deformation. But here we're just good. We even got a factor of safety built in. All right, so that's kind of how to read these numbers. But this means whatever this length is. So now this number is the fractional change in length. So this beam lengthens by 0.125%. If you can think of things as a percent, easier than the fractions of a whole. But what this says is this is an equation that's dimensionless, but it says that the change in length divided by the original length is going to be this number. And so I can rearrange that equation to get the change in length if I wanted to, because we know the original length. Okay, hell yeah. And Cool. And yeah, so let's just see what they do. But it's just good to talk about what these terms are. And then, so we have the halfway point is the neutral axis. So the distance from the bottom, where the strain is, that elongation, to the center is 3 inches. Okay, so now it says determine the radius of curvature. And it should just be geometry, you know what I mean? Like, hey, this arc length on the lower surface is the original length plus this percent change in length. It increased, you know what I mean? So I would take the original length and then multiply the original length times this and then add those two numbers together. Yeah, so it's just kind of fascinating how it's not too difficult, but just maybe because these numbers are so small, it kind of makes it mentally difficult. All right, so it says, note, this beam has a relatively large deflection because its length is big, 96 inches, compared to its height. Its height is 16. No. The length is 96 divided by 6. And I guess that's 16. Who knew? How would we do that? What's 96 divided by 12? I don't know. What's 96 divided by 24? Oh, hell yeah. I remember that one. 96 divided by 24 is 4. And so this has to be, yeah, I think I can get there to 16. Just kind of working backwards. Okay, sweet. And the strain is going to be this 0.00125 compared to a max strain that still can take of 0.002. And this strain is pretty large, you know what I mean? It's getting up there. It's half the max, over half the max. It is about the same as the yield strain for ordinary structural steel. Oh, and then my bad. But for the strain, typically, you know what I mean, for good quality steel, it should be 0.002 and 58,000 psi. And that'll give you a modulus of elasticity of 29 million. So that's what I use. I use 0.002, 58,000 pounds, and then you get a modulus of elasticity of 29 million. Those three terms come up way more than saying that, you know what I mean, and maybe that's the upper end. Maybe that's the ultimate strength. I have no idea. But, okay, yeah, so I have to double check my reality on that one. But, yeah, so yield is where, hey, if you're past this, you're going to get permanent changes in, it's going to be bent out of shape. All right, so let's move on to the solution. So curvature, since we know the longitudinal strain at the bottom of the beam is this 0.00125. And any term that's kind of small, like I think the brain just doesn't even want to like read the, you know, if it was, hey, 3 inches, I can just read that out. But, oh man, this is brutal, you know what I mean? And what do you do, 0.00125? I think that's the best way. You could say it's 1.25 times 10 to the negative 2. That's not, you know, I don't know. Exponents as decimals don't help me either. So, cool. And so we know this strain. And since we also know the distance from the neutral surface is this 3 inches, and to the bottom its y is negative 3 inches because the y-axis is positive up. We can use equation 5.4. So let's see what equation 5.4 was. Okay, so we have the strain. We know that. And we know the distance to the location of that strain is negative 3. So we can either find the curvature or we can use either one of these equations. So let's just see what equation they use. So they use the fact that strain, let's get it over here, is equal to negative y rho. Oh, I better check that out. All right, hell yeah. So we're back, and yeah, I guess I just had to take a pause because, I mean, do we, like, how do we know we got this equation? Well, we went from this picture that if we do have a moment does create a part of a circle. Even if we just take a small little slice and we can put the moment as close, and I put 4 molecules of iron, you know what I mean, just Fe, and a moment is 2 forces. you'll have two forces on the top inward and then two forces on the bottom outward. And these opposing forces can be equal to those moments. So we can take a beam and just break it down to its, the smallest components we could have. And what happens is that if we have these two molecules get closer together and these two get farther apart, this line, which used to be straight, now they say it rotates. I just say it maybe slants. And this one slants the other direction, and you get a triangle to form. And because this is just a portion of a circle, or you could say that if we extended these lines, they would meet somewhere. Cool. And then we can say that even just this little segment is a part of a circle. And you can prove that if the moment stays the same throughout here, we're going to have another 4 molecules. They're going to get crunched in the same and stretched the same. And so we're just going to have all these trapezoidal shapes one after another, and you're going to get a smooth, continuous arc. And we've talked about that in the proof, that a circle is a constant change in angle. And let's see if I can, it's good for me to talk through these concepts faster than 3 hours. But if I have a sheet of paper with a 90-degree corner, I can put it right down here, and I can have the tangent right there. And then I'm going to go pin it to the center of this circle. And when I do that, then I can rotate that sheet of paper up to this point. And what happens is that sheet of paper played out this change in angle, but also what happens is that this angle, if this was flat or neutral, this angle, the change in angle, so this tangent now has a increase in its angle that's equal to d theta. And you can do this for a circle from the bottom, and then with that same sheet of paper, and then roll the sheet of paper up, pivot it about the center of the circle all the way up to 90. So then we would sweep an angle of 90, and then our tangent, the bottom surface of that paper, also swept out 90 degrees. Cool. So that's proving that moments, if you have a pure moment, creates a perfect circle. Now, if you have a moment that varies linearly, still, if you break it down to a small little segment, basically the moment on this side is going to be the same as the moment on that side. It's going to be fractionally different, just a little bit, but if this gets down to the slices are infinitesimal, basically the moment's going to be the same. And so at some point between this little segment, it is going to be the curve of a circle. But for pure moment, it's just pretty sweet because we just have a circle. We're going to identify the neutral axes, and then we can just use the equations of a circle. If I know this angle that's caused by this moment, then and then here we don't even need to prove too much of anything. We can just, we need to prove that an arc gets formed, and then the top surface is going to be crunched, the bottom surface is going to be lengthened, and there's going to be a place in the middle that's going to be neutral. That is where we're going to place our y and x axes. And so, and then we just know from geometry, if that's the case, we just know from geometry of a circle that this is going to be the neutral axes, and it's not going to change in length. The length is going to be this original length dx. And as we move, and if we're setting this as our y value, as we move y all the way up to our radius, if we have y is equal to the radius rho, we're going to be at that that junction, that the center of the circle, O, capital O prime. And now our distance is going to be 0. And so that's where we get the equation for, first off, we just need the equation of, this line as a function of y. So if this line was at halfway, like a distance of half the radius, well, this line would be half of dx. And so I'm not going to spell that one out just because I'm kind of slow at it, but you get this equation, and you basically can do it. I just do it based on those two. If I throw in y is equal to 0, I'm going to get dx. So the equation must be dx. And then if I throw in y as a positive rho, I'm going to get 0. So the equation must be like dx minus, minus dx, with this being y divided by rho. So that's the equation for this line. At any value of y, if I come up here in the y direction, I can know the length of this arc. It's going to be dx minus y rho dx. And so that's where we get that. That length of that line is dx minus y rho dx. And this is good. No, I'm just going to take, even if I take an hour for this one, I'd never, especially with proof problems, you should never do a problem without going back to the proof and kind of going step by step through it. So now we have the length of, if we go up a distance y, we know the length of this line. We could know the length of this line. But what we want to know is the strain. We want to know its change in length divided by the original length dx. And so that 1-2 punch is how we get strain. So cool, let's say I know the length of this line. It's going to be that equation. I want to know the change in length, which is length final, that's what this is, minus length initial. So we're going to take the equation that we just came up with, and then we're going to subtract dx. Well, check out the equation. This equation has a dx already in it. So we have dx minus y rho dx. And now this is length final. We're going to subtract length initial, which is dx. And then so these dx, so then we're just left with this term. And that's going to be the change in length, which is cool. But strain is change in length divided by the original length. So, so the change in length is length final minus length initial. We just did that and got that negative y divided by rho dx. And we have to divide the change in length by the original length dx. So cool. So we get this little thing, negative y rho dx, and we got to divide by dx. And that's our strain. That's how we get such a simple equation. But I think this one is a little bit tricky just because it looks like there's nothing to it. And then we just specify that radius of curvature is 1 divided by rho. All right, so so then they just rearrange the strain equation. This would be strain is equal to negative y divided by rho. They just rearrange it to find the radius, and that's going to be our, and don't think this negative is part of the equation. That's why the strain, when we went with positive curvature, we were saying if this is the curve, the radius is in the positive y direction, so this is a positive value for the radius. And we already know that because our curve is this way. But our strain, when we throw in a positive value of y, it crunches. And so the length reduces, and that's going to be a negative value for the strain. That's kind of associated with negative change in length. So that's why our strain equation was strain is negative y divided by rho. When rho is positive, and I go positive rho means that's the curvature. You know what I mean? So positive k, positive rho means that I have a smiley face. I'm setting my y-axis to be vertical, and so I'm going, and the radius is in the positive y-axis. But if I go in the positive y-axis, I get crunching of that beam and shortening. So that's where this negative comes from. Cool. So that's why even just something like this is kind of difficult to be like, what do these negatives mean? I want to know that I know I have positive curvature, so this has to be positive. The equation has negative, and then the y value is going to be, well, I just, from this given problem statement, it says I know the strain is going to be a positive, it's going to be a lengthening when y is negative 3. So those are the two values that I know. So we have negative 3 inches divided by 0.00125. These negatives cancel, and like I said, we get a positive value for rho. That means we have positive curvature. The y value, the y-axis is always positive up, and that means our radius is positive up. The center of the circle is up. And so here's our radius, 2,400 inches. And I guess they switch right back to feet, you know what I mean? And I guess that's fine. You can find a value and then switch it to feet if you want to. But just know that if you're working through material mechanics problems in U.S. customary, you want to be in inches and pounds until you get an answer, and then you can switch it. But even just right here, they wanted, you know what I mean, to get radius of curvature, you'd be 1 divided by rho, so that would be 1 divided by 2,400. But they just do 1 divided by 200, and so they get this as 0.005 feet to the negative 1 feet. Inverse feet, sorry. These results show that the radius of curvature is extremely large. Oh yeah, so this is the radius of a circle. So when we have a beam that's 98 feet long and we put a moment on both sides and it bends, if we cut out a circle, we would have to cut out a circle that was 200 feet. You know what I mean? So big as a base football stadium. You know that cutout of that paper circle you would need to hold in a football stadium just to kind of like, you know what I mean, view it. And that's what makes a lot of these deflections are really small. But for this, we don't have to use any small angle. I don't think so. I don't think we have to use any small angle because this angle's in radians, and we know our value of rho, and we know our arc length. You know what I mean? And we know our arc length at 2 different locations, the neutral axes, and we know it at the bottom axes. All right, so let's see what they do for this next part. These results show that the radius of curvature is extremely large compared to the length of the beam, even when the strain in the material is large. If, as usual, the strain is less, the radius of curvature even gets larger, with lower deflection and lower moments causing, so the radius of curvature you'd have to cut out a bigger paper circle to fit the curve of that bent beam. Deflection. As pointed out in section 5.3, a constant bending moment, pure bending, produces a constant curvature, so it's a portion of a circle, throughout the length of the beam. Therefore, the deflection curve is a circular arc. From that second figure, 5.8b, we see that the distance from the center of curvature, capital O prime, that's the center of the circle, to the midpoint, C prime. So now we're going to be to the midpoint, and this radius of curvature is from the midpoint, the neutral axes, to the center. So that's what we're talking about. So from the center of the circle, O prime, to C prime, to the midpoint of the beam, C prime, of the deflected beam is the radius of curvature, rho. And the distance from O prime to point C, that's, what is that, the top surface, on the x-axis is rho cosine theta. Let's see where that is. So they're saying, the chord. So not the top of the beam. Is that if you turn this into a chord, so now we have a right triangle. You know, I mean, it shouldn't be too hard. We have the hypotenuse is the radius of curvature, it's rho, and then we know our angle. I don't know, do we know our angle yet? I don't think we know our angle yet, but we at least have a right triangle. And with the right triangle, if you know two things, you know everything. So at some point we probably know our angle, because I probably know this total angle from the deflection. So hopefully they get there. But what they were saying is that, hey, we can find this distance. That's the cosine component. So if, let's say I just know this angle theta, then this distance from here, O prime to C, is just the cosine component of the hypotenuse. So that's going to be the hypotenuse, which is the radius, rho. So this is just rho cosine theta. It's just the percent of the hypotenuse in the cosine, the adjacent direction to that angle. And I always think of sines and cosines as percentages of this hypotenuse. The hypotenuse is always going to be the larger number. Cool. So so that's going to be rho cosine theta, where theta is the angle BO prime C. So I guess we can, so we have B O prime C. So yes, just one of these angles. Cool. This leads to the following expression for the deflection. Now, how would you find this deflection? Well, we know this total distance from the center of the circle all the way to the neutral axis, we're calling C prime. That is going to be, and this is fascinating. They should actually draw this larger because this beam has thickness. It's 6 inches thick. And the neutral axis is where C prime is. So, but where is C? I mean, is that taken from the chord from the neutral axes? I think it is. So, yeah. So I'm just going to say A and B are also on the neutral axes. And we know this distance is rho cosine theta. We know the radius rho is from the center of the beam to the center of the circle. And so what I'm interested in is the distance from this line to the top of the beam, which is a little bit, what is it, a little bit less? Because if I know, and this from trigonometry, this is what I do. I was just like, well, let's go the whole distance, and this is going to be rho. Now I'm at the middle of the beam. Now I'm going to subtract 3 inches. Now I'm at the top of the beam. And now I'm going to subtract this distance, which is rho cosine theta. And cool, now I have delta. So let's see what they did. So they said that delta is rho 1 minus cosine theta. Oh, so that's interesting. So they just kind of took... Oh man, yeah, like where are they saying A and B are? Because are they saying A must be the very top? Are they saying A is the top of the? Yeah, I mean, didn't they get that a little bit wrong? Because the beam does have thickness. And are we interested in delta from the center? Yeah, maybe that's what they're asking too. And the deflection delta of the beam. I would consider the deflection, I don't know, what are they considering the deflection? I mean, I would consider the deflection, I don't know. Yeah, point A to point B, and then just this distance drop. So no, they probably got it right, because I was saying A and B were at the neutral axis. It's not. It's at the top of the beam. So yeah, that probably jives. So we're going to have point A at the top of the beam and point B at the top of the beam. But rho is not from point A. Rho is from the neutral axes. So that's kind of interesting. But this chord length, I think they're taking from point A. Point A and B are at the top corner of that beam. That they should specify. And I'm losing my voice. All right, hell yeah. So we're back, and I have a better idea of what's going on. So, up here, point A is the top of the beam. And so we can have that down here, but the picture is so small. So A can be the top of the beam, and B can be the top of the beam. But this axes, Y and X, is still through the neutral axes. And that's going to be this chord. So this chord is through the neutral axis. And so if we have the distance... Oh, I thought I had this. Yeah, I would do this a little bit different. I would make sure my chord is at the top at point A to point B. You know what I mean? So back to this picture. So I would do it different than this example. I would take my chord to be from here to here, and then the deflection to be this part of the chord. But if we do that, this is the radius that we just found, and we already found that. And so the distance from the center of the circle to point A is rho minus 3 inches. And so if we did that, so let's come down here. If we say that from the top of this chord to the top of the beam at A to the top of the beam at B, if we do that chord, this radius to that top point A is going to be rho minus 3. That means that this has to be rho minus 3 in parentheses times cosine theta. And then the deflection is going to be the total radius all the way to the center, from the center of the circle to the neutral axis. That's going to be rho. Now we're going to have minus 3 to get to the top surface. So we're going to have rho minus 3 to get to here, and then we're going to subtract that cosine component, which is parentheses rho minus 3 end parentheses cosine theta. So cool. So we have rho minus 3 minus in parentheses rho minus 3 times cosine theta. And that gives us that deflection. All right, hell yeah. So that is the discrepancy. So I would say that is the displacement between the top of the beams, you know, points A and B, and then the surface of the beam. And so that's interesting. But maybe they don't call displacement that way. Maybe they do say the chord goes from the center of rotation at A and B. So they're going to back to this. I don't know, but they already specified this is point A and B. So, but maybe for this example problem, they're choosing this as the point where deflection is taken. So they're drawing a chord from this neutral axis to right here, and they're saying that this distance is the deflection. And so fair enough, which is slightly different than this chord. If I come up here to this chord and then go down to here, that deflection is a little bit, is it more or less? That deflection's a little bit less. And so that's kind of interesting. So maybe the true definition of deflection is from the center. So, you know, you take your neutral axes and make a point on either side of the neutral axes, draw a chord, and then you're just worried about the lowering of the center of that neutral axis. And I wish they would have specified that, but it's not even specified in any of these sections. But it's just fascinating that that's the way they're choosing to do this example. And sometimes textbooks are that way. You're just like, well, if the textbook did it this way, there was probably a rhyme and a reason, even if they didn't specify what that was. So hell yeah. You're taking the chord from the neutral axes to here. And then we're going to say the deflection is and even here, if we zoom in close, we'll be able to see that arrow goes from the chord to the neutral axes. And so, but over here, it doesn't look like this chord, this Y and X, is drawn. Over here, yeah, I can kind of see the top of that beam peeking out. All right, hell yeah, there was someone at the door, but we're almost ready to move on. So this chord is going to be from the neutral axes, and this deflection is from that chord to the neutral axes. And so then it works, you know what I mean? So then you're going to have your radius rho from the center of this circle to the neutral axes. That's going to be the hypotenuse. We're going to find this angle in a second. And so this length is going to be rho cosine theta. That means that this deflection is going to be rho minus rho cosine theta. And we can factor out the rho, and that's where we get the deflection is rho times 1 minus cosine theta. Cool. The other thing that they're going to do, which I don't even think they need to do, because we need to find this angle. But we already said that we're going to take rho from the neutral axes, and the neutral axis is the length of the beam. The beam crunches up on top, stretches on the bottom, but at that neutral axis, it's the same length. And so, yeah, it's just kind of fascinating. And so, so we know, and so we're gonna. I would take this whole thing to theta, be the easiest to visualize, because if I knew this angle in radians, and then I multiplied it by this radius, I would get this arc length, and that's going to be length L. So 2 theta times rho is equal to L. And so, so therefore 1 theta times the radius is equal to L divided by 2. And so, and then you can find theta, because if theta times radius is L divided by 2, we can just solve for theta. That's going to be L divided by 2 divided by the radius. So let's see where they get theta. Theta is the length divided by 2 divided by the radius. So yeah, they have it totally spelled out right here. And it's just fascinating that they're going to take the inverse sine of this. But now they just say, for practical purposes, we may consider sine theta is equal to theta in radians. But now this is a faux pas, because you don't need to do that anyway, because the definition of the neutral axes means that the length is, because right here they just said, hey, let's just assume that that this distance from this support to this support is L divided by 2. Even after we deflect it, this roller is going to roll in. So if we have large deflections, yeah, this thing is just going to roll in. So the actual distance of this chord is no longer the distance L. And so, because, yeah, that's just fascinating, because they're trying to find theta from the sine component. If they knew the sine component, and they're going to say this is L divided by 2, they could find, and we know the radius. Now we know 2 things about a right triangle. We know everything about it, so you can find this angle. And that's going to be the inverse sine of L divided by 2 divided by rho. So that's where they get that. So they're going to say this is theta is the inverse sine of L divided by 2 divided by rho. But you don't even need to take the inverse sine, because it's because the angle itself, this radius goes through the neutral axis right here, and then this radius also goes from the center of the circle to the neutral axis. So this is an arc length of a circle, and we know that theta in radians is going to be, this arc length is radians times radius is arc length. And so we know theta 100%. We don't need to do a small angle approximation on that one. So it's just kind of interesting. Cool. So you get theta is 0.02 radians. And awesome. All right. So I guess we didn't really read through that. So let's read from here. Deflection. As pointed out in section 5.3, a constant bending moment produces constant curvature throughout the length of the beam. Therefore, the deflection curve is a circle. It's a circular arc. And then from that figure, that second figure, we see that the distance from the center of that circle to the midpoint, C prime, of the deflected beam is the radius of curvature. And the distance from the center to the distance C, which is the chord length from the neutral axes, on the x-axis is rho cosine theta, where theta is that angle, and then this leads to the following expression for the deflection at the midpoint, and we already went through that. So the deflection at midpoint is delta is equal to rho times 1 minus cosine theta. For a nearly flat curve, and then this is where they do that approximation. For a nearly flat curve, we can assume that the distance between the supports, because it's curved, that distance between the supports is going to be reduced, but they're just going to approximate it. It's the same length of the original length of the beam. Therefore, that triangle this triangle BO prime C, so that's what they're trying to show, is, that triangle BO prime C, well, yeah, theta is that angle of BO prime C. This leads to the following expression for the deflection at the midpoint. And so that's where we have, therefore, from triangle BO prime C, we get sine theta. So the sine component is equal to the sine component divided by the radius. So sine of the angle is the sine component, is the opposite, divided by the hypotenuse, and that's going to be the radius rho. Substituting these numerical values, we get sine theta is equal to 96 divided by 2 divided by that radius of 2400, and then this number is 0.02, and that is 100% accurate. The angle is 0.02. It's not approximately. They do a small angle approximation, but they didn't need to, like I said. So note that for practical purposes, we may consider sine theta and theta in radians to be equally numerically because theta is very small angle. But I just don't think they need to. I think it is an arc. You're taking it from the neutral axes, and you already found the radius. So you know what the angle is, 100%. So now we substitute this angle into equation 5.5. So that's going to be this. So now that we have this angle of 0.02 radians, we can solve for the deflection. And so that's what they do. So the deflection is the radius rho, 2400 inches, times 1 minus cosine, and cosine 0.02 radians is 0.9998, very close to 1, but we have some discrepancy. And because this number is so large, this discrepancy gives us a deflection. Cool. So we get a deflection of 0.48 inches, almost a half an inch for an 8-foot span. So it's pretty decent. This deflection is very small compared to the length of the beam, as shown by the ratio of the span length to deflection. And that's true as well. If I was standing on an 8-foot beam that was just like a chunk of metal, and it only deflect a half an inch, I'd be like, hell yeah, that's pretty stout beam. Okay, so now what is this? Length divided by the deflection. What are we trying to find? This deflection is very small compared to the length of the beam. Yeah, so length divided by deflection. Maybe this is just a number that we attribute. So as shown by the ratio of the span length to the deflection, 96 divided by about 0.5, that's going to be about 200. Cool. Thus, we have confirmed that the deflection curve is nearly flat in spite of the large strains. Of course, in figure 5.8b, the deflection of the beam is highly exaggerated for clarity. So yeah, all those diagrams are exaggerated. Note, the purpose of this example is to show the relative magnitudes of the radius of curvature, 2400, the length of the beam, 96, and the deflection of about a half an inch. However, the method used for finding the deflection has little practical value because it is limited to pier bending, which produces a circular deflected shape. More useful methods for finding beam deflection are in Chapter 9. Yeah, so I guess you're just never going to have a beam in pier bending. It's an anomaly. You know what I mean? It's an ideal where it's like mainly you're going to have a beam with a car driving across it, and the weight's going to be in the middle. You're going to have downward forces or downward loads that are going to induce moments, and that moment's going to vary linearly. It could vary parabolically. A lot of things can happen. A lot of things compared to just pure bending. Okay, so there you go. There were some interesting things about this one of like where to put these chords, you know what I mean? But we kind of deduced where they did. They took this chord from the neutral axes, and then they said this distance delta for the deflection was from the top of this chord to the neutral axes as well. And that's going to be rho, and then subtract this rho minus cosine theta. And then we use that to find theta, but theta is 100% accurate because this is the neutral axis, and it's in an arc, and we know the radius. So we know the radius of a circle, and we know an arc length of it. And so if I knew the circumference, I could, and we know if we know the radius of a circle, we know the circumference. So all I have to do is take this length, divide it by the circumference of a circle with 2 pi, with a radius of r, 2 pi r, and then that's going to give me the fraction of the circle. And I can multiply that fraction by 360 to get the degrees of this angle, and that's going to be this total angle 2 theta, or I can multiply it by 2 pi to get this angle in radians. So, hell yeah. Alright, so we're done with this one, and I'm just glad I have a video for tomorrow. So, thanks for joining me, and that's a video.